It's rough.
Well, I'll begin with a word of prayer. Ahem. Ahem. Yeah, that worked. All right, let's begin with a word of prayer. So, Dearly Father, we thank you for this day. I thank you for these students and their exuberance. Help them to understand what we're going over today. Help us to glorify you, what we do. And we just thank you again for your many blessings to us, Lord Jesus. Amen. So, yeah, time to start. So let me recap here. One-dimensional motion. Trash can's kind of far away in here. So the average velocity is the change in x over the change in t, right? And likewise, you could talk about average acceleration. It would be the change in velocity divided by the change in time. All right? But, and then of course we could break that down further, right? Like x2 minus x1 over t2 minus t1. These would be averages, right? So that we've been able to calculate since, I don't know, middle school or whatever, right? But what's interesting now is we can talk about constant acceleration. So let's work it out real quick. So we have a equals to a sub 0, that's a constant, right? And if that's equal to dv dt, we can integrate both sides, say from t1 to t2, and a sub 0 dt from d1 to dt2, and this gives us v of t2 minus v of t1 is equal to a sub 0 times t2 minus t1, right? In other words, you find if we let t2 equals to t, right, then that gives us v of time t is equal to, and let's let v of t1 just be equal to v1. That's like a common notation in here. So v of t will be v1 plus a sub 0 times t minus t1. So there you go. That's the velocity as a function of time in the constant acceleration case, right? Something interesting happens here in that you can graph that. All right, so if I graph that, v equals to, say, v1 plus a naught t minus t1, right? If I graph that, and if I look at, say, time 1 to time 2 there, something very interesting happens. So here's t1, here's t2, right? So I'm graphing time versus velocity here. What's the meaning of the area? Distance traveled, the displacement we called it last time, right? So delta x, or in other words, x2 minus x1 is the area, right? But what is the area of a trapezoid? So this right here would be what we call V2. This right here would be called V1. To find the area of a trapezoid, you take the average of the before and after, right? So I take 1/2 of V1 plus V2, and I multiply by the width here, which is delta t. So that's just geometry. And this gives us another handy-dandy formula for V average. See, because this gives us that change in x over change in t is V1 plus V2 over 2. In other words, I can come back up to the start of this lecture and I can say, well, this is also equal to V1 plus V2 divided by 2. When can I say that? Yeah. No, the velocity doesn't have to be constant. The velocity is changing. The acceleration has to be constant, but your heart's in the right place. Yes. So this assumes that dA dt is equal to 0, right? Which is a fancy way of saying the acceleration is constant, right? Now, so in terms of one-dimensional motion, of course we have this formula for the velocity as a function of time, but we also have this super nice relation between calculating average velocity in this fashion or calculating average velocity in this really different way, right? Add the before and after velocities, divide by 2. It's a totally different idea of averaging, yeah? And then what else can we do? Well, we can integrate again, right? Integrate again. So, of course, v of t, well, let me do it up here. V of t, I'll just say v is equal to v1 plus a sub 0 times t minus t1, right? And that's equal to what? That's equal to dx dt. So we can integrate that from, say, t1 to t2, dx dt dt, integral of v1 plus a0 times t minus t1 dt, integrating from t1 to t2, what happens? The net change theorem, right, on the left-hand side gives me, you know, right-hand side gives me x of t2 minus x of t1. So this integrates to x of t2 minus x of t1. And the other side, when we take the integral, we get v1 times t2 minus t1 plus a sub 0 over 2, you know, t minus t1 squared. We have to evaluate that one from t1 to t2. Okay, that's the integration here, right? So what happens? I anti-differentiated, used FTC part 2, right? The first part's so easy, I just integrated it, right? Constant integrated gives me the length of the integration region times the constant, in this case is v1. But the second part, well, when I plug in t1, what happens to this? It's just 0, right? So only the upper bound contributes, and lo and behold, we find the following. I'm going to let t2 equal to t, and then this gives us x at time t is equal to, and I'm also going to let x of t1 to be equal to x1. And this gives me x of t is x1 plus v1 t minus t1 plus 1/2 a sub 0 t minus t1 quantity squared. And there you go. That's one of the kinematic formulas, right? So if we have constant acceleration, this is how we find the position as a function of time. And also, of course, we need to know the initial velocity, right? Now, there's another way to write this formula, which you'll often see if you look at my lectures, which is that I'll write it like this. This is really, you know, I could write this as x1 plus like v1 delta t plus 1/2 a sub 0 delta t squared. So we could express it in that way. And sometimes that's convenient, right? In fact, truth be told, as you look at the solutions that I've written for this course and the notes that I've posted, right, you'll notice that a lot of times I take t1 equals to 0, and I just label some things with like a sub naught. So like continuing in this fashion, alternatively, we could write the following formulas. We could write like v is equal to v0 plus a sub 0 t. You could write x is equal to x sub naught plus v naught times t plus 1/2 a sub naught t squared. I oftentimes use these formulas, right? There's a few different ways to package the formulas. The important thing is that you understand what they mean, all right? And understand that these are a simple consequence of the calculus that you already know from like calculus 1, right? Any questions so far? So these are the tools that you use to solve constant acceleration problems, all right? Now there's more. There's more. There's also the timeless equation. Timeless equation. So the timeless equation we get as follows. So for constant acceleration, we have a sub 0 is dv dt, right? But we can do something sneaky here. we can trade dv dt for a derivative with respect to x in the following way. By the chain rule, we've got dx dt dv dx, which, if you tilt your head and squint and see, is actually v dv dx, which gives me joy to say. And then separate variables here. So we get a sub 0 dx is equal to v dv. And then we can integrate both sides. Now you're like, what is this dark magic that you're doing? The answer is I'm doing something from your Calculus 2 class in about 2 weeks, 3 weeks, depending on the schedule. But this you will learn in Calculus 2 soon. This is called solving a differential equation with separation of variables. Basically, we just solve for the differentials, put them on one side and the other side, and then integrate both sides. When you integrate both sides, to be fair, you have to integrate matching sides. So I would say integrate from x sub 0 to x sub f, and correspondingly I'd integrate from the corresponding velocities v sub 0 to v sub f. How do you integrate a constant times dx? Just x again, right? So this side integrates to a sub 0 times x sub f minus x sub 0. And the other side integrates to 1/2 v squared evaluated from v0 to vf, also known as 1/2 vf squared minus v0 squared, right? So lo and behold, we derive the following equation. Vf squared is equal to v0 squared plus twice a sub 0 times xf minus x naught. I refer to this as the timeless equation. Can you see why? It's got no time, right? So if you're solving a kinematic problem where you're just interested in some kind of relation between, like, say, velocity and position, the timeless equation might be the way to go, right? Because it circumvents the problem of, like, finding time like we did last time for that example that I took entirely too long on. So these are the basic ingredients for solving one-dimensional problems. You have your kinematic equations, you have your average velocity relation. If a problem requires the average velocity relation, it's a sneaky one, right? And then there are others that are nice with the timeless equation. Let me stop writing and just project for a bit here, because I want to draw your attention to something which perhaps I haven't emphasized enough yet here, which is I have posted notes for you guys, right? So, like, yeah, I mean, you're like, you don't follow the book. Guilty as charged, right? Guilty as charged. But what I do follow are my notes, largely speaking. Now, so like here, let me just take a step back here for a second. You guys should know where my notes are, right? So if you look at the initial course announcement, right, I link you to the course webpage, which is here, James Cook's University Physics 1 homepage. And you notice all the required homework is posted right up here. A playlist from a previous time I taught physics is here. You'll find different examples there. If you want to see me talk more about physics, there it is. Actually, I think, well, excuse me, that's for this semester. Here's the one for previous time, back in a simpler time. I guess I got 2 courses on the shelf there. But look down here, lecture 1, lecture 2, lecture 3, lecture 4, so forth, right? These are handwritten notes. They have examples. I don't have time to cover all of those in class, so this effectively serves as our book, right? Let me just be clear. This is our book. You need to look at these. You need to read these. I don't think I was forceful enough about that last week. My bad, right? I'm telling you now. It's not too late, right? Start a second week. Some of you are new to the course, so I should probably warn you there's a homework due Wednesday. It's going to take you more than 10 minutes. Let's see here. So, and it's turned in on paper in class. This needs to be said because it's weird, right? So anyway, where we are right now is basically we've covered lecture 2, lecture 3, working on covering lectures 4 and 6 today. Lecture 5, see, this is what I got out of order. Like last time I basically jumped ahead and did a little bit of lecture 5. I should really not have done that. My apologies. So like, it'd be better if I just literally covered the order of these lectures. I got a little bit out of order, and I did some three-dimensional stuff in here with you guys, right? And we'll come back to that probably Wednesday, all right? But anyway, so these are where the lectures are. You could just click their PDFs. You open them up wherever you want. So enough about that. So let's look at some examples from the lectures because, you know, I have to face facts. Like, I can't write out every lecture and every example in here, right? There's just not enough time. It's just the nature of word problems. So here's a good one. Example 3. But I'd like to talk through a couple of examples from lecture 4 with you, just to try to complete our discussion of one-dimensional stuff, okay? So here's a silly problem. Suppose Superman is a little slow due to the excessively cloudy weather shielding the warmth of our yellow sun. He flies back and forth at a speed of 500 miles per hour between trains on a collision course. So the trains have speeds of 80 miles per hour and 50 miles per hour respectively, and they begin 150 miles apart, all right? The question then is, if Superman travels back and forth between the trains, so he's flying back and forth trying to get people off the trains, right? And assuming that the time Superman for reversing directions is negligible, right? So he just stops the trains as they almost collide, since a reality TV show, well, you know, a TV show needs, a reality TV show needs a what? Shot for commercials that week. Okay. It's not a good sign when you don't remember your own joke, but let's see here. If it makes sense to you, if it's funny to you guys, good. So here's a picture. Sure. We've got train A and train B. They're coming towards each other. I've chose this one to be 80 miles per hour. I chose that one to be minus 50. Minus 50 because it's going to the left. All right? And then what I do is I write down the collision is when they're equal, right? X of A equal to X of B. So I put down what are the formulas here. So in this case, the acceleration is 0, right? So we just have velocity times time for our formula. So 80 miles per hour times t, or 150 minus 50 times t, because it starts over here. I'm putting the origin at the start where train A is, right? And then I set them equal, and that tells me what time they collide, which is at 1.154 hours. So how far did Superman go? Well, here the average velocity is useful, right? Because what I know is that he's always flying at 500 miles per hour, right? And how long is he doing it? Well, 1.15 hours. So I just take Superman velocity times that time, and that tells me Superman traveled 577 miles as he's flying back and forth between these silly trains. So here's an example which makes good use of the average velocity idea, right? Solving this problem without average velocity, in other words, like figuring out what's the time Superman gets to the first train, and then what's the time he gets back to the other train, and then back and forth, and like calculating those, it would be very much hard. That would be much harder, right? Whew, goodness, I don't even want to think about it. It would be an infinite series, actually. Whew, let's not even think about that. And then in my notes, listen, I thought that I should work this out for you today on the board, so I did that, okay? But that's a derivation of the formulas I've already written on the board. There's the timeless equation. Here's an example, a really simple one. Suppose a car has brakes which apply a constant deceleration of minus 2 meters per second squared. If the car has an initial speed of 20 meters per second, then what's its stopping distance? This problem is made to order for the timeless equation. So we have the final velocity is 0. The initial velocity is 20. The acceleration is minus 2. We're interested in delta x, so solve for it. 100 meters, right? It doesn't have to be hard. It's just mostly me writing in here that makes it hard, right? Because it's hard to write everything I write, isn't it? How fast did the car in example 4 stop? Well, we can figure that out from this other kinematic equation, right? The final velocity is equal to the initial velocity plus acceleration times time. I know the final, I know the initial, right? I know the acceleration, so 10 seconds, right? Let's go to and here's the picture I already drew over there, right? And here's what you'd actually have to do to work it out rather than, I used a trick with the area. of the trapezoid. Like here would be direct algebraic reasoning for the average velocity is 1/2 v1 plus v2, right? So conceptual checkpoint, right? Velocity is the rate of change of position. Acceleration is the rate of change of the velocity, right? And you got to be careful because there's a temptation to just sort of lump all these things together. I got a picture over here I wanted to look at. Where'd it go? Here it is. I think that thing I just skipped over was I solved the velocity as a function of position for constant jerk, which is just a quirky derivation in the notes, right? Okay, so here's some different cases, right? If we have a ball going up, right, like I was talking about last time, the acceleration goes down, right? So the acceleration is downward, yet the velocity is upward, right? And on the other hand, cars speeding up, you could have the acceleration is this direction, the same direction as the speed, right? But the acceleration doesn't have to be the same direction as the velocity, rather, right? If the car is braking, the velocity is forward, but the acceleration is backwards, right? So we can't, the directions of the velocity and the acceleration, they're independent, okay? That's all I'm trying to say here, so. I talk about Tipler in here. Tipler is a very nice book that we had to stop using because it was like too intimidating for the students. It was just like really, really technical in some sense, but I don't know. I don't like Tipler either, if that's any consolation, but it was what we were using at the time I wrote these notes. Let me, so here's a more complicated example, which I'm going to skip over. And here's a really complicated example about a parachutist dropping, opening a parachute, and studying like the motion in stages, right? It would take me 20 minutes to work this carefully. Here's one I'll actually work through. So 2 stones are dropped from a cliff, all right? The second stone 1.6 seconds after the first. How far below the top of the cliff is the second stone when the separation between the stones is 36 meters? So do you understand? You're dropping one and then dropping another. At some time later, the distance between the things you've dropped is 36 meters. All right? And in fact, it tells us after 1.6 seconds, oh, excuse me, when it, blah, blah, blah. No, the question is how far below the top of the cliff is the second stone when the separation is 36 meters. It doesn't tell us when that time happens, right? There's like a lot of things missing here. So how do you work this kind of problem? Well, you write the kinematic equations and just sort of work through it. So what I did here was I said stone A is dropped. I can't read my writing. I said stone B is dropped at t equals to 0, and stone A is dropped at t equals 1.6 seconds. So the formula then for A is this y0 minus 1/2 g t minus 1.6 seconds, because its motion starts at 1.6 seconds, all right? Whereas B starts at time 0, so that's why I have minus 1/2 gt squared, right? Now here, y0 is the height of the cliff. I don't know that, right? What am I trying to find? I'm trying to figure out how far below the top of the cliff is the second stone when the separation of the stones is 36 meters, all right? So let's see here. So this is just the setup, right? I know that's 36 meters. So going on here. So what I'm given is that YA minus YB is 36 meters. At some time I don't know, right? But it's equal to, on the other hand, minus 1/2 this plus 1/2 that. And then I do algebra, right? And this gives me a quadratic equation in T, which I can solve. I get 2 solutions. The one of which is interesting is this one. Wait a minute. Or does the t's cancel? I think I might have thrown away a extraneous solution here, because usually quadratic gives you 2 solutions, right? But 1.4936 is the one of interest. And so then I can look at the difference between YA and YB, which, by the way, would be 1/2 gt squared. Excuse me, not B, that's a sub-zero. YA minus Y0 is 1/2 gt squared, which then is 10.94 meters. So they were 10.94 meters below the edge of the cliff where they were dropped, if the second one is 36 meters from the first one that was dropped. So It's a kind of complicated problem, right? I mean, this is a hard homework problem if you haven't seen somebody go through this example and these ideas, right? So you use the equations I did at the start of class plus algebra to figure these things out. And you have to just write down, you have to pick some things. Like, the problem doesn't tell you where to put the origin, right? The problem doesn't tell you where to make time 0. That's your invention for these kinds of problems, right? That's part of physics, is this is creative aspect to it. You have to set coordinates in time, right? Mathematics is different, right? Like in calculus, we force you down a certain path, right? Like we're graph this function on the xy plane. We're setting where the 0 is, and you have less freedom in math. You have much more freedom here. This is a nasty problem. Suppose a subway car accelerates as it leaves the station. As it passes a certain person waiting for another train, it takes 2 seconds for one car, 1 second for the next subway car to pass. If the cars have length 10 meters, then how fast are they traveling as they begin to pass? So here's a picture, snapshot. Here's Mr. Observer, time 0, there he is, right? After 2 seconds, 1 car has passed, right? After 3 seconds, 2 cars have passed. So how do you figure out the initial speed of the train just as he's starting to pass the observer? So the way I did it was to use the average velocity idea. See, because the average over the first, let's see here, 2 seconds, is I take the initial velocity, which is v0, the final velocity, which is v1. So 1/2 of the initial and final velocities, that's equal to the average velocity, which is what? Well, what's the average velocity? Well, he's gone 10 meters in 2 seconds, right? So the average velocity is 5 meters per second. And then over the second time period, going from here to here, let's see here, we've got, he's gone 10 meters, let's see here, v1 plus v2, right? Divided by 2, and then in this 2 seconds, in 1 second, going from t equals 2 to t equals 3, that's 1 second, right? So the average velocity is 10 divided by 1, which is 10 meters per second, so that gives us this equation. And then you can look at the average velocity from the start to the end. That gives you a third equation. See, because going from the start to the end, the final velocity is v2, the initial velocity is v0, so I have v0 plus v2 divided by 2. What's the average velocity overall? Well, I've gone from t equals 0 to t equals 3, 3 seconds. How long? Well, 20 meters, right? So 20 divided by 3, so I have that. And then, my friends, we have 3 equations and 3 unknowns, and you've all had college algebra, so you can solve 3 equations and 3 unknowns. And when you do that, you get 5/3 meters per second. Yeah.
And we're assuming constant acceleration here.
Yep. Yeah, this is assuming constant acceleration, right? Fair enough. Yeah, if we didn't know that, I don't think you could solve the problem. Yeah. Did I ever tell you guys the joke I heard about math in the subway? I was at a Dunkin' Donuts in New York City a couple years ago. Well, some years ago. And there's this guy who's coming in, this little kid. Well, he wasn't too little. He was actually fairly big. But he was kind of giving the people behind the counter trouble, just being a punk and so forth. And this old fellow, he must have been about 70. He's like, he started talking to him, trying to de-escalate the situation, and so he said to him, what's your favorite subject in school? And the kid's like, well, math, sir. He may or may not cert him. I forget if he cert him or not, but he said math. And he's like, oh, really? I got a problem for you. You want to hear it? The kid's like, okay. Are you ready? You paying attention? And he's like, okay, yeah. It's like, so there's 10 people on a subway car, right? It gets to the station, 2 get off, 3 more get on. You got it? It's like, yeah. All right. Then they drive, they go to the next station, and then 5 get off, and 7 get on. You got it? The kid's like, yeah. All right. You paying attention, right? Okay, good. Then the subway car goes again, and then 6 people get on, and 2 people get on. You got it? All right, this goes on. This goes on for a couple minutes, all right? And then finally, at the end of all this, you know what he asks him? He says, how many times did the Subway car stop. I love that joke. And then the kid stopped harassing the employees, so it was good. So, all right. So we're now officially a half hour behind my schedule, okay, guys? So like I said, today was projectile motion, right? We are now starting projectile motion, okay? Just so you know, that's where we are. Projectile motion is lecture 6. All right, so let's work it out. What's projectile motion? Right? Do you guys know? Like what? A what? A blob? Like this, right? Nice catch. Good. So why is it projectile motion? What's the situation with the tennis ball? She's not even flinching. What's the deal? Well, the ball is just under the influence of what when it's traveling? What? Gravity, right? So the basic thought here for projectile, well, oh, you said air resistance? So you've had differential equations then. Because that's what we need to treat air resistance, right? We need to be able to solve differential equations that depend on the velocity, right? Which means we need techniques of calculus, which you guys don't know, unfortunately, to really treat friction. And even then, it's more complicated than that. But the essential idea is just this. The acceleration is 0 minus g. And so we're gonna be two-dimensional here for a bit. So two-dimensional is reasonable because, I don't know if you noticed this or not, but whenever I threw the ball, pay attention. If you look at it, rats. If you look at it, there was a plane where the motion happened in, right? Like, if I throw it, there's a particular plane where that motion's happening in, right? It's not going this way or that. I'm not throwing a curveball, right? So the motion's in a plane, so it suffices to treat projectile motion in a plane, and that's what we're going to do. We're going to assume that basically the motion looks like this. We've got like our initial position here. It's at some point, say x0, y0, right? The initial velocity is something like this. We typically say that it's at angle theta, right? And then what happens is it flies, right? Under its own influence. We ignore what? We ignore air friction, yeah? And then we can ask interesting questions like, how far did it go? You know? So here's x, here's y. We're assuming that the motion of the projectile is in the xy plane, and we're assuming that it's clear, because we've done experiments before, that the acceleration is constant, 9.8 meters per second downward, like that, right? So mathematically, that's this, all right? And let me just derive it with calculus. So here's how we do that. I'm going to convert to a different notation to make life easier. This is really just minus gy hat, right? And that's equal to what? That's equal to dv vector dt. Integrate both sides. From time 0 to time t, I get v is equal to v sub 0 minus gt y hat. Integrating once. Integrating a second time, this is dr dt. The position as a function of time. Integrate again. I get r is equal to r0 plus t times the initial velocity minus 1/2 gt squared y hat. And there you go. This is the position as a function of time if we use a vector formalism. All right, but let's not just do that, right? Let's talk about how to break this up into like components. So this is my v sub 0 up here, right? And if you look at that, we can break that into two pieces, yeah? There's the x component and the y component. So this piece right here would be v0 cosine theta, and then the vertical piece of that would be v0 sine theta. So some notation I'm going to use for that is simply this. V sub 0 x is v naught cosine theta, and v sub 0 y is v naught sine theta. And what happens if we, put this into components, right? Here R is, it's got your x and your y in it, right? And what's this equal to? X naught, y naught, plus t times v naught x, comma v naught y, minus 1/2 gt squared times that. Well, that gy hat is really, excuse me, well, that's just 0, 1, okay? So I'm just writing out what the blue boxed equation means in terms of its component breakdown. And so from that, you see we get x is equal to x0 plus t times v0x, right? But if you don't mind, I'm just going to get to the point here. What is v0x? It's v0 cosine theta, right? And what's my y equal to? Well, it's equal to the initial y plus t times v0 sine theta minus 1/2 gt squared. And so there you go. These are the kinematic equations for projectile motion. So we can ask interesting questions, right? Like, what's the max height that you get to? Can you guys tell, how would we figure out the max height? What's that? When the velocity in y is 0, right? So let's figure out max height. So that's going to be where dy dt is equal to 0. That gives us a critical point for y, which is to say that vy, which is what? V naught sine theta minus gt is equal to 0. Now, I guess I didn't write that down yet, shouldn't I? I should write that, shouldn't I? Here's the other formulas. Vx is equal to v0. That's it. So there's your formula for the velocity as a function of time. For the x, it's kind of boring, right? Whatever x velocity it has at the start, it has at the end. That's it. Because we're ignoring air friction. Vy is v naught sine theta minus gt. So there's your formulas for x and y, right? Okay, so the time to the, this is the time to the top, right? So t top apparently is v naught sine theta over g. So what is the actual max height? Y max would be equal to y0. I use the formula, right? Plus t top v naught sine theta minus 1/2 g t top squared, which is, goodness, I should have put in the t top already. Fine. So I've got y0 plus v naught squared sine squared theta over g minus 1/2 g times v naught squared sine squared theta over g squared. So what do we got? We've got y max is equal to the initial y plus 1/2 v naught squared sine squared theta over g. So there you go. That's the formula to find the max height for projectile motion. Does that make sense? All we did was we found the time when the velocity was 0, which is the highest point, right? And then we plug that into the y formula to get the y max. What's the max rate? What's the range? What's the range equation? In other words, so like typical notation is, well, let me start over here. So suppose we start here. The question is, how far does it take to get back to the same level? All right, so basically I'm just assuming y sub 0 is equal to 0, right? This distance here would be typically called r, the range. So the, again, we're launching it at angle theta with initial speed v0, right? How far does it go? So let's see here. We've got y is equal to, let's see, now we're putting initial y as 0, right? So we've got t v naught sine theta, yeah? Minus 1/2 gt squared. And what can you tell me? 1/2 gt squared. So we're trying to find the range here. So you guys tell me, what can you tell me, like the time we're interested, what's y equal to at the time we're interested? We're interested in when the projectile gets back to here, right? So what's y equal to there? 0, right? So we just need to set this equal to 0. That will give us the time of flight overall, right? Now here, this is a special case. We're assuming that we're beginning and ending at the same height, right? You've got lots of homework problems and other examples in my lecture 6 where that's not the case, all right? This is a very special case. Beginning and ending at the same height. Factor t out. You've got v naught sine theta minus, g over 2 t equal to 0. So this is a quadratic equation, but we just factored it. So the solutions are what? T equals to 0, or t equals to 2 v naught sine theta over g, right? Which one of those are we interested in? And does this make sense? Tell me why this makes sense in view of the last derivation that we just did for max height. See how much time it took to get to the top? V naught sine theta over g, right? And now I've made the situation symmetrical. So the time up and the time down are the same, right? So the time up, v naught sine theta over g. The time back down, v naught sine theta over g. So twice that is the total time of flight. Makes perfect sense. In this initial problem, that wouldn't have been equal, because if my initial y is different than my final y, the time back down is longer. The time to the top would not match the time down because there's an asymmetry there, yeah? Okay, this one here, so how do I figure out the range? Well, go back to the x equation. What's the x equation? X equals x naught plus v naught cosine theta times t, right? So x minus x naught would be equal to v naught cosine theta times the t, which is 2 v naught sine theta over g. X minus x naught, that is the distance traveled, right? That's the range. And so lo and behold, we found the range formula is, 2 v naught squared sine theta cosine theta over g, which I'll write over here again. R equals 2 v naught squared sine of twice theta over g. So these are kind of like the easiest versions of these projectile problems is when somebody asks you, what's the max height? Or what's the range, right? These you can actually just go back to these formulas, and as long as the context is correct, you can apply these to solve the problem pretty fast, yeah? Where did my sine theta cosine theta go into? What happened here? Why is it v naught squared sine 2 theta? This is trigonometry, right? Question, what's the max range? How can you make v naught squared sine 2 theta over g as big as it can be for a given fixed value of initial speed?
Set the angle to 45 degrees.
Set the angle to 45 degrees. I think that'll work because that's what's going to give you this sine 2 theta term equal to 1, right? And that's as big as sine can be. All right? Okay, so one last fun thing for... So listen, it would be good for you to read lecture 6, all right, before Wednesday. I'll probably spend the first couple minutes Wednesday just talking through some examples in there, like I did today. But since we still have a minute here, let's do something fun. Let's figure out how fast this gun shoots, all right? So I reset this thing to meters, so that's going to be better, all right? So I'm going to need you guys to... All right, somebody write this down for me, 12.16 meters. I'll write it down, 12.16 meters, all right? We need to calculate. So, all right, so you guys, I need you to... all right, so we're going to... I need you guys to kind of... try to get this on the level best as I can. See, this is a little bit, I mean, if we had longer, we could do better. Let's see here. Oh man. See, do you see something about that ball? Do you see what happened? What happened? See that? I don't think this even means anything. These things spin. As you can see, if like, oh yeah, it's spinning. So like the first one actually curved up. Sorry. I was hoping we could figure out how, my idea was, if you have a gun, you shoot it like this, right? Let me just make up some numbers. And it dropped. Suppose it dropped, like 0.5 meters and that far. Then the question would be, how fast did you shoot the gun? That was the question I had in mind. How would you solve that? I won't. So the way I would solve that, think through it. I won't write it. I'm not going to write it. I'm just going to talk, okay? The way to solve a problem like that is you can figure out the time of flight. How? How can you figure out time of flight without a timer? So I'm initially shooting it right here, right? It drops 0.5 meters. How long does it take to drop 0.5 meters? So here's something. I said I wasn't going to write. Obviously that was false. Yf squared is equal to Vy0 squared minus 2g delta y. That's the timeless equation just for the y velocity, which is relevant because the y is, if you look at the equations here, right? Y has constant acceleration of minus g. So this is the timeless equation for the y velocity. And if you tell me that the delta y is 0.5 meters, that specifies that the final y velocity has to be whatever it is. What's the initial y velocity? It's 0 because I shot it horizontally, right? So from this, we can figure out the final y velocity, and then you can figure out how much time it took, right? Because vyf is equal to vy naught. Good grief. I'm trying. My labels here. Golly. What I'm trying to say here, sometimes I'm putting the 0 first and the y second, and I can't make up my mind. So my bad. But anyway, my point to you is, we know that the initial was 0. We know that the final is whatever it was from the above equation, which means that we can figure out the time. And then once you know that, what can you do? Then you can figure out the x velocity, right? Because you had that much time to go that far over, so you can track back and figure out what the x velocity is from that. And once you put that all, the x velocity is, the initial x velocity is the speed which you're shooting the bullet, right? So if the bullets weren't so awesome and curvy, we could actually do this and it'd be meaningful, but I think it's actually meaningless because there's a lot of air resistance involved in that, actually. Anyway, I shut up. Thanks, guys. Don't forget to get your homework.